This is the video on the routine for the binary solution. Over here on the left is the routine that is used to do the binary solution. Over here on the right is data in lists for the binary solution. The first list, this box at the top, is for the bit price. Here it says the price of the first is 1, the second bit is 2, third bit is 4, and the fourth bit is 1. I happen to know that these are all for the first item. If you sum them up, you'll get the value of 8. It says in this problem that the first item can be in the solution up to 8. In other words, 0 times to 8 times. And what this means here is here the factor is 1, here it's 2, here the factor is 4, and here the factor is 1 again. You add up its factors and you get 8. The next item could go up to 6. Here we have it in 1 time at its price of 4, 2 times price of 8, 3 times for the price of 12. So altogether, it's 1, 2, 3, 4, 5, 6. It can be in 6 times. And all the other items follow the same way. They have an entry of bits to get up to the value that they're allowed to be. That is their quantity. So this box has to do with the bit price. The 2 boxes below have to do with the requires. Over here it refers to requires. The first box is if the bit is going to be brought into the solution, it's going to require 11 of the first part and 12 of the second part. You see, it's minus them. They're minuses. It's taking the parts away. The next box, though, says at offset 400, it's putting the parts back into what it calls over here part left. That's a list of the available parts for each of, in this case, 8 parts. And also in this solution here, there are 8 entries for each bit. Remember up here it says the first bit was 1. Well, the parts that are needed, if it's that bit, is 11 of this, 12 of this, and then the rest of the 8, it doesn't require any. But when it's in 2 times, it requires 22 and 24. And then 4 times, here it's 44 and 48. But these lists are 8 offsets apart because there can be 8 parts needed for each of the bits. The one below is the same values but positive. That means it's returning them back to part left because that particular bit is being taken out of the solution. So it has to put the parts back into part left. Alright, now we'll go over to the routine itself. Over here. First it sets NS to 8. Well, that is the number of parts that there are in the list. Well, this add L instruction here and the one down here is add list, and it's adding or subtracting the requires. We know here at offset 400 it's adding back to the part left the 8 values because they're positive here, and down here it's when it comes into the solution it takes those parts out. Well, let's go to the next instruction. Branch if not equal the bit value at PG. Now PG starts at 0. And over again we're going to be at set back to 0 down here. Alright, it checks to see if it's a 1. Well, in the beginning all the bit values are 0. So it's not going to be a 1. So it's going to put a 1 in it down here. It's going to go to AE and put a 1 in it. But up here it was a 0. The bit values are either 0 or 1. They all start out at 0. It starts out at the beginning. It says, can I turn that bit on, and if it can, it turns it on down here. But if that bit is on already, and this is a binary number, that means we're adding 1 and 1, and that becomes 2. We can't have 2 in a position, we have a carry. So what it has to do then, it has to say, well, this bit value is now set to 0, and I'm going to do a carry. I'm going to subtract its value from the solution because it was 1. Now I'm making it 0. I have to take its value away from the solution using the bit price over here. And then I got to add back its required parts because it's out of the solution now. So required at 400 Q down here is going to add the parts back. Then it says if P G is greater than or equal to the bit count, we go to AI. We've carried all the way to the end. If we carry the bit all the way to the end, well, there's nowhere else to go. We went as far as we could. It goes to AI down here, sets the task to 4, and exits. But it's going to be a while before the bit carries all the way to the end. Well, what's coming down here next? It says if not, well, then I'm going to add 1 to PG. I'm going to go out to the next bit. And I'm going to add 8 to QG because these are 8 apart. And then it goes back up to AC. Does the same thing again. A bit is going to carry over as long as the bits are 1. But as soon as it finds a bit that isn't 1, it's going to go down here to AE. And then it's going to set the bit value to 1. Well, that means that one's coming into the solution. So then it adds to the current income the bit price it gets from over here at that offset of PG. And then it takes the requirements away from the parts left. All right, so it's using these here. Then it says, branch if less than or equal the current income to the best income. It's saying that if this isn't a better solution than a previous one I have, I'm going to AG, that's down here. It also is going to go around a loop to check to see if any of the lefts have gone less than 0, meaning the solution requires more parts than we have. So it checked every one of them from offset 0 to 7, that's 8. It checks to see if the part left is less than 0. If it's less than 0, this solution is not allowed, and it's going to go to AG down here. However, if it is an allowed solution, well, then it says, well, now the best income is this current income. And I'm going to save the bits that are on right now because they're the bits for that solution. So it's saving the bit values, that's what we're changing up here, saves them in best bits. Then it falls down here and it starts all over again. It sets PG to 0 and it sets QG to 0, but it adds 1 to the loop count. And then down here it says if that's less than 1,000,000, go to AC. It's going to be less than 1,000,000 because we don't have that many operations we have to do. But it goes back up here to AC, adds another bit. You see, we know it's going to stop because it got to the end of the bits. Like down here. If PG is greater than the bit count, we went to AI, remember, and we ended. Alright, so this is the binary solution. The reason it is slower than the gray code solution is here we saw we had to go around and make more than one changes when we changed the bit. As long as we had carries, we had to go and change again and again until we didn't have a carry. We had to find a 0 bit. So the binary solution takes more time because it's bringing more than one in or bringing more than one out of the solution each time it makes a change. Alright, this is the video on the binary solution to the integer programming problem.